Hi, my name is Drew Parson. I'd like to give you a brief introduction to my research. One of the ideas I look into is adhesion at surfaces, adsorption of molecules or ions at surfaces, and how we can use quantum mechanics to understand that. Many of us like to spend time by the water at the sea. Have you ever stopped to ask the question, how do shellfish and mollusks bind to rocks? Or to the hulls of ships? Binding of marine organisms is actually quite a big problem for the shipping industry. It's called biofouling. We get a similar problem in medicine where bacteria form biofilms in tubes inserted into patients. Elsewhere in biology, we have questions of isolating proteins. By adjusting salt solutions, we can cause proteins to aggregate and precipitate out so we can purify them. The question of particles binding also comes into how drugs can be delivered to targeted tissues. These questions are not only in biology, also in the coal and the mineral industry. One technique used to separate valuable ore from junk rock is froth flotation, where mineral particles of one kind will bind to air bubbles and be floated over, while the others will sink to the bottom, so that two can be separated. In water treatment, also in sewage or industrial wastewater, we want to separate solid particulates from the water so we can get a clarified, clean water out from the stream. Also with electrodes, we have questions of corrosion. We also want to use electrodes for catalysis or for energy storage. This also involves questions of ions adsorbing to electrode surfaces. So what's the physics behind these surfaces? In many cases, the surface has a charge. So you can think of the question of two like charges. Do they repel? We have this idea of like repels like. But when you put these particles into a solution of water with salt, that salt solution also contains counter ions, which complicates the picture. We might end up with these particles attracting rather than repelling. So attractive or repulsive forces, what's actually going on? We need to combine different areas of the physics in order to get the big picture, the whole picture. So the surface charges, the charges of ions, that's part of the story. We use the theory of electric fields to understand that. But we also need to track the concentration profiles of ions adsorbed to the surfaces. And to do that, we use an area of physics called statistical mechanics, which describes the distribution of particles. What we find is that the adsorption layer itself, we can think of it as acting like a cushion, which generates a repulsive force, keeping particles apart. Another element that comes into play are quantum mechanical van der Waals forces. You may have heard of van der Waals forces as being related to shifts in the electron cloud around molecules, allowing gas molecules, otherwise inert, to pull in towards each other. The same applies with the interaction of ions at a surface. So we may end up with, for instance, a negative ion being pulled towards a negatively charged surface. From the electric charge alone, they would be repelled, but because of these quantum mechanical forces, they can be attracted. So the overall behavior is a complex, subtle balance between these various elements. They may stabilize or destabilize particles suspended in a fluid, depending on the particular conditions. They may impede or aid the formation of thin films. One study which I've made is applying these ideas to gas molecules trapped inside ice. This is a material called a clathrate, which is formed in the tundra and also under the sea. And so it has a question for melting and climate change. What we've seen from the theory is that a thin layer of ice is stabilized around carbon dioxide clathrates, which will tend to seal the gas molecules in. Around Methane clathrates, though the ice layer is completely melted, which raises the risk that the methane will escape into the atmosphere. Some current directions which I'm looking on is the distribution of charges in polymer films. This helps us to describe the biofilms I mentioned earlier. We can also use it to design functional coatings, smart paint if you like, or as a new design for energy storage. The study of ions adsorbing to surfaces is also important for electrodes, which again comes back to understanding what's happening in energy storage devices and also in other redox reactions such as corrosion. That's a brief glimpse of my research, and I'd be delighted to give you more detail and to get you involved with this research. Thank you.